This presentation is devoted to fully nonlinear solution of the problem of ice-water structure interaction. This work was done in collaboration with Professor Bayoni, Tatiana Khavapasheva, Emilian Parau, and Alexander Korobkin. We consider two problems. First is the flow in the channel covered with obstruction on the bottom, covered by elastic sheet. The second problem is the flow submerged below ice sheet in the fluid of infinite depth. We use the assumption that fluid is ideal, incompressible, flow irrotational. The elastic sheet enough thin to apply Casseret theory of hydroelastic shells. Hydrodynamic pressure on the interface from liquid side is the same as pressure bending the elastic sheet. Flexural gravity waves may extend to infinity in both directions. The flow is steady. First, we consider this problem of flow in the channel with obstruction. We solve this problem using integral hodograph method, which to constructing the function of the complex potential. Real part of this function is velocity potential, and imaginary part is stream function. Both these functions satisfy Laplace equation in the fluid domain. On the bottom surface, stream function is 0. On the interface, stream function is a unit because we choose the reference parameter as depth of channel and the inflow velocity. The Bernoulli equation on the interface accounts the presence of ice sheet, so pressure is calculated as shown in equation 6. So at infinity, flow is uniform, so and is equal to the inflow velocity. So I recall some case step of classic hodograph method. It is we need to find function W on Z, but it is difficult because we don't know conformal mapping of the potential plane onto the physical plane. Instead of to resolve this difficulty, Zhukovsky and Mitchell proposed to introduce auxiliary parameter plane or zeta plane. They use it typically upper half plane. Then they considered two functions, complex potential as function of the parameter zeta, and complex velocity or function omega, which is logarithm of complex velocity. If these functions are known, then velocity in the flow region and the flow boundary can be obtained in the parameter form as shown here. We choose first quadrant as a parameter region, and complex potential plane represents just a strip. It's very simple, and we immediately can find function W on Z, complex potential. It is logarithm, and its derivative also easily obtained. Next, we need to determine function complex velocity. It's much more complicated problem because there is variation of the argument of the complex velocity and magnitude on the interface. So we need to solve this boundary value problem for the complex velocity. We need an integral formula which recover a complex function from its boundary on the real and imaginary axis of the first quadrant as shown in equation 11 and 12. So I need to say that because flow is steady, velocity direction coincides with the slope of the bottom. To derive this integral formula, we use Chaplygin's special point method. It is based on two. First is two fundamental things. First is the symmetry principle, and second, Liouville theorem. Riemann symmetry principle says that if we have a function defined in region R1 and straight segment of the boundary sigma, we can extend this function into the region R2 through the straight line. We can provide two kinds of boundary condition. We can provide that imaginary part of complex function is 0 on the straight line, or magnitude of function is equal constant 1. In first case, we need to put in the symmetric point P2 value conjugated to the value at point 1. For the second case, we need to put in point P inverse value and provide the same argument. If all singularity in the extended complex plane are known, then we can recover the complex function easily using Liouville theorem, as shown in equation 13. Here all zeros of order alpha, all polars of order beta, and C is real constant. So from this equation we can find function fz. Now we derive integral formulae to solve the boundary value problem for the complex function f, which we imply complex velocity. So on the real axis of the first quadrant it is given function g. On the imaginary axis it is function rho. So we discretize the real and imaginary part into the intervals, and each intervals we assume that argument is constant, and it changes by step when we go from one interval to next. Same for the imaginary axis, here the magnitude of the function. So if we have a step change of argument, we can easily determine a singularity at this point, as shown here. Now we need to extend the first quadrant to the second quadrant, and we need to extend it so way to provide magnitude of the velocity constant. So at the interval. So we need to put the additional singularity at symmetric points of inverse order. Then we need to extend upper half plane to the lower half plane, and additional singularity appears at points symmetric to the points eta j. We consider function g in order I, and then magnitude of this function, function g, becomes argument of function g in order I. We apply the same technique as previously and determine all singularities in the lower half plane, and totally we determine all singularities in the whole plane and the real and imaginary axis. So we can write, gathering all the singularity, we can write this equation according to Liouville theorem. It is constant. Then we rewrite the products in exponential form, and we obtain the integral of the function g and v. Here rho, sorry. Here the step change as shown as differential. So this is integral formulae solve the boundary value problem 14. We can easily verify it substituting zeta equal to psi or zeta equal to eta, I eta, and obtain the real argument and magnitude as given in the boundary conditions. So using this integral formula, we can obtain final expression for the complex velocity. Then using this relation between complex potential and complex velocity, we obtain the mapping function. Almost solve it. But small problem is that here there is a logarithmic singularity because it comes from the function complex potential, derivative complex potential. So we come back to the complex plane and consider complex potential as an independent variable. So we substitute this parameter into expression for the complex velocity and obtain this expression. This it is necessary because due to logarithmic singularity, computer cannot accommodate real numbers in some range, because if real number too big, extend this range, so computation not possible. So this complex velocity still contain a known function d beta and the logarithm velocity. So we use the shape of the bottom to determine function d beta df. Bottom is given, bottom of the channel is given by function s, and the derivative of the spatial arc length coordinate on the bottom is just obtained from the derivative of mapping function, and we obtain it integral differential equation as shown here. It is very fast convergent equation. Now we need to determine velocity magnitude on the interface, much more complicated problem. If we will go similar, evaluate the velocity direction, then differentiate it, we arrive to the hypersingular integral equation, which is challenging to solve. Instead of that, we use a spline approximation of the interface at some intervals, and then calculated curvature and its derivative, and we can evaluate pressure coefficient from liquid part and pressure coefficient from elastic sheet, so they should be the same. So we can obtain system of nonlinear equations which is solved using collocation method. Before calculation, we need to determine range of root number corresponding to subcritical and supercritical flow regimes. Usually dispersion relation is obtained from solution of linear problem, but we can use some trick to obtain dispersion relation with elastic sheet using dispersion relation for the free surface flow. So here the Bernoulli equation, differentiated Bernoulli equation, and without ice sheet we have this equation, and we know from solution for the free surface that Froude number is related to wave number as shown here. Then with elastic sheet we have this equation, and we assume that velocity magnitude behave on the interface same way with and without ice sheet. From this assumption we equate the right hand side of this equation and obtain characteristic equation for the elastic sheet. It coincides with known with dispersion relation obtained from linear solution of the problem. Here shown results of calculation subcritical flow. For different Froude number and different height of the abstraction. We can see as height of abstraction increases, the how to say the change of the deformation of the interface also decreases. But there is one moment. So if Froude number 0.5, we can calculate only maximum height of abstraction 0.2. We are not able to calculate height abstraction larger. So this is limit. Here shown limit for different Froude number. For 0.4 is the height 3.3, And when we approach to the critical fruit number, the maximal height of the abstraction reduces. And here shown how they behave iteration process. Only small change in the height of the abstraction from 0.32 to 0.33 change the behavior of the convergence. Second part of the presentation is about ice supercritical channel subcritical flow. In this case, we have two waves. One is a gravity wave, as usually, which extends downstream, and we obtain new wave, which we call elastic wave due to elastic sheet, which extends upstream. In calculation, we need to, as in formulation of problem was shown, we need to have uniform flow at infinity in both upstream and downstream. So we need to depress this oscillation. It is done using artificial term as dump as shown here. It is applied at some regions downstream and upstream. It is shown from these results that this term does not affect solution in the region where this term is absent. Here shown ice supercritical channel subcritical flow, fruit 0.9 and fruit 75. Fruit 0.9 is closer to the critical value 1. And we can see that in this case, and two height of abstraction, 0.5 and 0.7, red and the blue line. What we can see that in case of gravity wave downstream quite large amplitude, but upstream elastic wave is small amplitude. However, the bending moment, and we cannot see elastic wave downstream. But it can be seen in the moment where the appears elastic wave effect on the throw of the waves interface. So this is pressure coefficient along the. We cannot calculate a larger height of abstraction because here dashed line shows local fruit number. Local fruit number reaches 1, that it is channel supercritical flow and not possible to get convergent solution. If fruit number approaches to critical fruit number, the wave length, elastic wave length approaches gravity wave length, and they interact and very complicate behavior of the interface and correspondingly bending moment and pressure coefficient. For fruit number supercritical, more than 1, without ice sheet, only two solutions, soliton wave can be observed and perturbed wave. So one way. In case of the ice sheet, we found that there is elastic wave extending downstream. Here shown the behavior of the elastic sheet for supercritical flow as function of the thickness ice thickness. We can see there is a maximum for the amplitude oscillation, and also there is amplitude oscillation of the pressure coefficient. Here is shown a region of existence of the steady solution. It exists below the line, and it is has two critical fruit number. First is fruit number 1, based due to the flow in the channel, and another critical fruit number due to elastic sheet. So as the thickness elastic sheet increases, these two first critical fruit number approaches due to the elastic sheet approaches 1 also. So this is explain why height of obstruction quite small to get the steady solution. Another problem is body submerged beneath ice sheet. I very shortly talk about this because way of solution is similar, only show the difference. This difference, main difference is that flow domain is doubly connected domain, and we need to make a cut connecting body and interface. In this case, for doubly connected domain, we use Jacobi double periodic, quasi-double periodic function. We use properties that obviously that values of velocity is the same on the both sides of the cut that correspond to the vertical sides of the rectangle. This lower side of rectangle correspond to the body, and upper side in the correspond to the interface. The periodicity is pi and p tau. So this is a definition of Jacobi zeta function. So we derive integral equation to solve this boundary value problem. Is given velocity magnitude on the interface, velocity argument on the body, and periodicity on the cut. So then we complex velocity, applying Chaplygin method, we can obtain derivative of the complex potential, and we have unknown parameters a, b, c, tau, and k, which we, for determination of which we have same number of conditions. Kinematic conditions to determine the, again, shape of the function d beta dxi is obtained from the given function of the determining the shape of the body. So we have the similar integral differential equation. Similar problem to determine the velocity magnitude on the interface. We do the same and reduce the problem to the system of nonlinear equation. Again, we determine the dispersion equation without solving linear problem, just considering wave behavior, velocity magnitude along the interface. So for the free surface and for the with elastic sheet, and equating these two sides, we obtain the dispersion equation for the case of ice cover. Here the shown velocity response of the interface in subcritical flow regimes. Here shown also when we in this case sense of the height of obstruction play depth of submergence. As body closer to the interface, it causes larger disturbation of the interface. So we can see that similar behavior, similar features we have for this problem as for the previously. Here shown the supercritical flow, and again when Froude number is far from the critical Froude number, the wavelengths for the elastic sheet very different from the wavelength for the gravity wave, and we can see superposition of these waves. Then we approach critical Froude number to reduce Froude number. We can see how the similar results for the bending moment and for the pressure coefficient. Again, we approach to the critical Froude number, then we can see that wave due to elastic sheet decay downstream, but it keeps the same amplitude upstream. So, and finally, we show the results for the Froude very closer to the critical Froude number, and very complicated behavior of the interface in both directions. It's due to the superposition of two waves which lengths are closer each other. So this is again existence of solution when we approach to the critical Froude number. The depth of the submergence should be larger and larger, far from the interface. So conclusions. Fully nonlinear solution flexural-gravity waves in a channel and in the infinite depth fluid are presented. The interface exhibits superposition of the elastic and the gravity waves. The elastic waves decay downstream. Decay becomes more slowly as Froude number approaches critical Froude number. And there is a region in the plane depth of submerged Froude number where the steady solution cannot be obtained. Thank you for your attention.
Thank you. Oh, yep. Okay.
Maybe I can speak.
Yeah, you are first.
In your model, you take the case of zero viscosity, and we expect that probably there should be some viscous effect, particularly near the bottom. Do you know how you could consider that, or could it be taken into account in some way? Or?
Yes, of course, real fluid change the results, but actually it can be included. In that case, we should consider viscous inviscid interaction. We introduce a boundary layer and interface between inviscid layer and boundary of the boundary layer, boundary of boundary layer.
And there could be also viscosity on your membrane itself, on the ice sheet. Probably that could be the dominant effect, the dissipation in the sheet propagation. Do you have that? Or I don't think so.
Dissipation, of course, but yes, of course, viscosity causes dissipation. It's clear, but in case of the elastic sheet, it is very small effect. Very small. Effect is larger in case of broken ice. Yes, and we published a paper with broken ice and introduced damping due to the loss of energy, considering broken ice as viscous layer, and then viscous layer absorb energy. So.
Okay, next question.
Yeah, in the case of the submerged body, is there any arbitrary circulation that you can add in, or is the circulation?
Yes, yes. Thank you for your equation. Now here is system of equation, and last equation include circulation around body, and we can put this is free parameter of solution, and we can put circulation as we wish and obtain corresponding results.
So it can be assigned.
Yes, the results were published in GFM actually for different kind of circulation.
Okay. Any other questions? We still have a few minutes, 1 minute. As to dumping, Christoph, there is dumping. If you show the very first slide, there are two regions of dumping, right? Where? No, not this one. Yeah, before that. No, with the region of dumping.
Maybe here.
Yeah. Kind of modeling. Okay, any other questions? No? Then thank you again.
Thank you.